Deep Learning Lesson 6 ICP. There are 4 tasks provided as the number of neurons for the encoding layer. The size it is we are using fashion MST and MNIST dataset. It's a 3-dimensional dataset. The second dimension and third dimensions are 28 and 28. As a product of 28 and 28 is 784. We have taken input shape as 784. As we have to encode it, I was doing under complete encoding. As a for under complete encoding, the number of neurons and the input number of neurons. So I have taken 32 number of neurons for encoding, so that each neuron takes 24.5. That 784 values in 32 we are using under complete encoding here. For the input layer I was using shape and passing 784 here. For the encode I was adding encoding layer with 32 as the number of neurons, and activation is relu, passing input layer as an input to that. Next, coming to the decoding, I was using 784 as the input, and output size should be same. I was using 784 as an output size too. As it is an output layer, I was using sigmoid as an activation and passing input as this encoded layer. I was reconstructing it like mapping input dimensions, input layer and an output decoded layer. This is input and this is output. I was modeling and compiling with optimizer as binary cross and matrix as accuracy. Now I was, as this is done, just fitting is required to fit the data as it is unsupervised. We are not worried about why. We are worried only about the X part, like labeling part. So for the X train, Y train, X test, Y test, I have taken fashion MNIST load. I was, as it has 0 to 255 values in the data set, to convert them into between 0 to 1. I was dividing by 255. It was nothing but scaling of data, as I need, if it is between 0 and 1, for example, if a value gets 0 0.6, it needs to be 0 0.6. It should not, a floor should not be occurred, and as it is 0 0.6 nearby 1, the value should not be 1, it should be 0 0.6. So is the reason I was converting it to floor and dividing by 255. So I was scaling the data here. uh, as I said sorry, as I said previously, that my data set is of 3 dimension. The second dimension, third dimension, 28 into 28. I was converting it to 7 to 84. To convert that, to make that in the data set, I was using this part like product. Using as it is an empire product on that, on the shape of 1 to the end. Like it means here the second dimension, third dimensions get multiplied. It generates 784. It on the complete data set, on the train and the test. I was fitting it on extrain and extrain a process so that it transfers to 5 times with batches of 256. For it divides the data into 256, 256, 256, like each, and then runs for 5 times. Shuffling is true. For validating data, I was using X test. Training on extrain and validating on X test. For prediction, I was using an X test. As we have trained here with autoencode as an object, I was using autoencoder object. Predicting the X test, I was plotting a graph. Like if I take 50th row, it was something like a full hand shape. When I plot it after the prediction, you can see that it looks almost similar. Now adding one more hidden layer to autoencoder. I have added the hidden layer after the input and before the encoding layer. Input in between encoding layer and the input layer, you can see that I added a hidden layer here with the input number of neurons as 512 and activation as relu. I have taken 512 because it will be between the 784 and 32. As we are doing under complete encoding, I thought of putting less number of neurons rather than 784. So is the reason I have taken 512. uh, as as it works in the the code would be in between, and the, as we have added hidden layer here, we should add the hidden layer in the decoding part too. As it is between encoding and input, it should be between encoding and decoding here. So is the reason I have added another hidden layer with the same features. As it is, as it acts like a mirror. The features should be same, like fighter number of neurons and activation is relu. uh, I would use the same signal activation is 784 neurons, same input and output neuron should be same, so it's a 784. I passed this hidden layer as an input. For this hidden layer, I passed this input layer, and for the encoding, I have used this hidden layer, and I have modeled it and compiled this scaling of data, downloading data, like converting it into one dimension, like flattening into one dimension, 28 and 27 at 50 same here. Fitted the data and predicting on the X test. Uh, this is how again I have taken the 50th sample. It is same the t-shirt here. Now after reconstructing the image, after adding the hidden layer, it looks almost similar with hidden layer, without hidden. This is without hidden layer. This is with hidden layer. It looks almost similar. Coming to question, same with adding noise to the autoencoder. I have taken noise factor of 0.5 here, and on the X-train, I was applying this noise factor using the naive bias, some like np.random.normal with local scale as one size as its own shape, with noise factor adding as 0.5 and multiplying this complete thing on the X-train and Y-train. We are to perform this. I have taken another X-train noisy. I was fitting on X-train noisy using X-train, validating on X-test noisy using X-test noisy. Like this is image before applying noise. Before applying noise, it looks like this. After applying noise, I have taken here X-train, means before noise. After applying noise, X-train noise, it looks like this. You can see there is a lot of we have taken 0.5 as a factor as 50% of noise. It looks almost blur with complete. We cannot figure it out. Like now applying prediction on that. Uh, when I apply prediction, like this is initial thing before applying prediction, the 50th sample. After applying prediction, you can see that after applying noise, so it looks similar. After decoding, after deconstruction, it looks almost similar as this previously. So you can see it looks almost similar even after adding noise too. In noise, you can see this, you cannot find anything. After deconstruction, it looks almost similar. Now plotting loss and accuracy using the history object, I have stored here this fit. I have stored it in history here, this particular fit model. And now I was using that particular thing, that particular autoencoder object, and I have seen the metrics. It was loss and accuracy. Now when I apply it, using the history object, history accuracy and loss, when I was plotting for loss and accuracy, this is how the graph is. Now coming to the bonus question, visualizing the compressed version of the input layer in the middle layer. Now we can know, we have come to know that the input layer, we can add hidden, it's up to us whether we are adding hidden layer or not. Input layer, encoded layer, then the compressed thing, and decoded layer, right? So we want to check the compressed version. So I have removed hidden layers here. I have taken just input layer, encoded layer, and decoded layer. Now I was encoding the model based on, as we need to visualize the compressed version of input layer. I was taking this encoded layer and input layer for modeling, input layer and this encoded layer here for modeling. I have compiled it and I have loaded the data. Now while I was predicting it for the second sample, you can see like this is how it looks for the compressed data. I was using this predict and calling this particular encoded images. This is how it looks. Thank you.